Show that negative 1 is a 0 of p of x equals x cubed minus 5x squared plus 2x plus 8. Find the other zeros of p and then sketch its graph. So to show that negative 1 is a 0, we need to show that x plus 1 is a factor. And to do that, we need to use synthetic division to show that when we divide by x plus 1, that gives us no remainder. So we can put the coefficients into the division symbol, bar, whatever you want to call it, and then we perform synthetic division. We bring the 1 down, we multiply, we add, we multiply, we add, we multiply, we add, and the remainder is 0. So what this tells us is p of x is equal to x plus 1 times x squared minus 6x plus 8. And while the original polynomial was not something that we were capable of factoring, we could try grouping because it has 4 terms, but that's not going to work out. Despite the fact that that wasn't factorable easily, the leftovers that we have here are factorable using the unfoiling method. So we need two numbers that have a product of 8 and a sum of negative 6. Those numbers are negative 2 and negative 4. So here we have 3 factors, and those 3 factors correspond to the zeros negative 1, positive 2, and positive 4. So we have shown that negative 1 is a 0 using synthetic division. We've then found the other zeros by factoring the remaining part, and we can use those now to sketch the graph. Our zeros are negative 1, 2, and 4. We also have a y-intercept of 8 because the constant term gives us the y-intercept, so that's going to be right here. Remember that we wanted to know in between these intervals whether the function was going to be above or below. We can see that in this interval it's going to be above just because of the y-intercept. For this one right here, we can evaluate the function at 3 to figure out if the graph is going to be above or below. And remember, we can use the remainder theorem to evaluate this function there using synthetic division. We just have to set up a synthetic division. We use 3 here because we're looking at x equals 3. And then when we go through the process, whatever the remainder is will be our function value. So we bring down the 1. 1 times 3 is 3. Negative 5 plus 3 is negative 2. Negative 2 times 3 is negative 6. 2 plus negative 6 is negative 4. Negative 4 times 3 is negative 12. And 8 plus negative 12 is negative 4. The remainder is negative 4. Therefore, our function value is negative 4, and we can plot a point right there. And then finally, because this is a third-degree polynomial with a positive leading coefficient, we know that we're going to be moving up when we go to the right and down to the left for our end behavior. So we can draw a graph that goes through these points and has the proper end behavior. And our graph is going to look something like this. Now, of course, these points that we have are not necessarily the local maximum and local minimum values. It might be going higher than that point and lower than that point. So you shouldn't always draw it that these random points that you get are the maximum and minimum values. But regardless, this gives us an idea of what the graph looks like. And we are accurate as far as the intercepts are concerned, as far as the end behavior is concerned, and as far as the intervals where our function is positive and negative are concerned, which is pretty decent. in calculus, we will look at how to find these local maximum and minimum values and end up with an even more accurate graph.